Okay, let's start. Today we'll look at gradient vector, and then next hour hopefully we'll start with minima and maxima. So let's see. First we want gradients, and we will use gradients to look at tangent planes. Okay. So this story started to understand the rate of change of a function of two variables. We looked at partial derivatives, and then we realized that partial derivatives calculate the rate of change either in x direction or in y direction. So we said what happens in other directions. So let's start from there again. So we have a function, say z equals f of x, y. Suppose the function is defined around this point. Okay. Then we consider a line like this. So suppose that a point here is x sub 0, y sub 0. Then you add to that a unit vector. Okay, say u1, u2. Here, for normalizing the result that everybody will get, we want this to be a unit vector such that the length of this vector is equal to 1. Okay, so we restrict f to this line. So this gives us a new function which we want to denote as f of t. Okay, so this function is evaluated here. So let us write this in one form. Okay, so we evaluate f at that point. So we write this. Okay, so once we have this, okay, let's say that u is pointing upward. So suppose this direction is u. Okay, because you will, if u points in the other direction, then algebraically we'll again write it like this. But when we look at the direction of u, it tells us in which direction we are moving as t is increasing. Okay, now you can look at this as a function of t. Forget about all the geometry. Now this is like t x-axis or t-axis. This is the origin. Your function has a graph on a curve over this, and we want to look at the derivative of this. Okay, so we want to look at the derivative of this in particular at t equals 0, which will correspond to evaluating this at x sub 0, y sub 0. So this is what we want to understand, derivative of this at t equals 0. So by chain rule, first I take the derivative of this with respect to its first variable, fx. Then I evaluate this at t equals 0. At t equals 0, I have x sub 0, y sub 0. Then I multiply this with the derivative of what I see as the first variable with respect to t. And here I get u1. And then I evaluate this at t equals 0. But this is a nice case. This is already a constant. But the general rule tells me that after I take the derivative of this expression with respect to t, I evaluate it at t equals 0. Okay, so here is a constant, so no problem. Then I do it again with the second derivative, with the second variable. So this is u2. Okay, so we look at this and we realize that this is a dot product. So this is fx, x sub 0, y sub 0, fy, x sub 0, y sub 0. I have this vector. I dot product it with this vector. Okay, now the surprising thing here at first is that I'm trying to understand the rate of change of this function along a direction, but this number these numbers that show up on this side do not depend on the direction. The direction only shows up here. Okay, so apparently this vector here is intrinsic to the function. It's a property of the function. We give it a name. Okay, so remember we called this the gradient. The gradient of f at x sub 0, y sub 0, and the notation was nabla f evaluated at x sub 0, y sub 0. This vector from here we already know is equal to the vector u. Okay, so the directional derivative is gradient of f evaluated at this point times u. Okay, so the directional derivative, or well, we didn't give it a name so far. Let's pretend that we don't have a name yet. The rate of change of this function along the direction of the unit vector u is this dot product. Okay, so the direction only shows up here, and this is a property of the function. This will always be there. You'll just change the direction. Okay, so we called this. So last time we called this. We called this number the directional derivative of f at x sub 0, y sub 0 in the direction of the unit vector u. Okay. Obviously, we don't want to repeat this whole sentence every time. We denoted notation for this. This is direction derivative of f at the point x sub 0, y sub 0 in the direction of the unit vector u. Okay, so every time you have a precise technical definition, then you allow yourself some liberties. Okay, so sometimes we talk about the directional derivative in the direction of a vector. The vector is not necessarily unit vector, but we agree that as a convention, when you are doing the calculation, you'll take the unit vector in that direction. Unit vector in the direction of a vector is just that vector divided by its length. Okay, so we call this in mathematics abuse of language, abuse of notation. Okay, so let me make this as a remark. If u is not a unit vector, we still write d u f x sub 0, y sub 0. What we mean directional derivative in the direction of this unit vector of f at x sub 0, y sub 0. Okay, so this is a convention, because as you know, when you calculate the length of a vector, it is square root of something in most cases in the denominator. So it's just crowded to write everything like this. So you just write a nice vector there, and in the calculations, this must be a unit vector. Okay, so you see now it is very clear that this is really a directional derivative. When you check what's happening in this direction, the number you get tells you how fast the function wants to increase in this direction. Then the next obvious question is, which direction is the best? Well, when we say best, it is either the largest number or the smallest number. Okay, so for that thing, we go back to this equation which we found. Okay, so next question was the following. Which direction gives the largest or smallest value for the directional derivative? Okay, So for this thing, obviously we start with the definition, or rather the formula we discovered here, x sub 0, y sub 0. This was the gradient dot product u. Okay, now when we have a dot product, we know that this can also be written as the length of this first vector times the length of the second vector times cosine of the angle in between. Here, theta is the smaller angle between these two vectors. Gradient of f at that point and the unit vector u. Okay, so if this is the gradient of f at that point, and if this is your direction, okay, so this is theta. The other angle is this one, it is larger. Okay, now we go back. Why did we write this? We wanted to look at the largest and smallest of these things. So you see that once the point is given, this is fixed. This is always 1. This is always equal to 1. So the directional derivative, the length, is the length of the gradient at that point times cosine theta. Okay, so no matter which direction we are looking at, this number remains the same. Only cosine theta is changing. Okay, so suddenly the problem collapses. We look at the minimum and maximum values of theta, and that gives us the direction. Okay, so when will this be largest? When cosine theta is 1, that's the maximum value. Cosine theta is 1 when theta is 0. Okay, so it means that this angle is 0. Well, this one is fixed. We are only choosing u. So if you choose u in the direction of the gradient, that's the direction where the function wants to increase fastest. Okay. Similarly, the minimum value of cosine theta is -1. So that's when you choose u in the opposite direction and you force the function to move this direction. Then the function decreases, and the decrease is fastest. Okay. So let me write that also, because even though these are trivial observations, they are very useful. Okay. So at this point, x sub 0, y sub 0, so we have this. Suppose this direction is the direction of gradient of f at that point. Okay, so let me emphasize this arrow. Okay, f increases fastest in the direction of gradient of f at x sub 0, y sub 0. Okay? So actually, again, by abuse of language, what we mean is if you just want to be absolutely pedantic, what we are saying is that the direction is gradient of this divided by the length of this vector. Okay, but we understand that. And this f decreases fastest in the direction of, in the opposite direction, so that is minus gradient of f at that point. Okay. So this was what we did last time. Okay, now since the ideas, there is only one idea here, numerical examples, I'll leave it to you, because you see, you get a function f x y, you get a point x sub 0, y sub 0. The question will be, in which direction does this function tends to increase fastest? Okay, you'll just take the gradient, okay, and you say in this direction. If you want to give a unit vector, then you divide it by its length. Okay, so that's the only thing you do. And as I mentioned last time, and the friend, somebody you sent me a paper on this. So these things are used in real life, but every time I say real life, it is not the usual real life. It is real life of you and me, scientists and engineers. So our lives is different. So in our real life, we use gradients. you want to find, for example, the maximum value of this function. If the function is complicated, the usual techniques, which we will start to see today, are difficult to implement. So, and sometimes you just want to get an idea. Once you get an idea about this, then you can refine your conclusions. So you start from a point. Okay, so one application of this. You start from a point at x sub 0, y sub 0. Okay, so you say, I suspect, okay, you examine the function a little bit. You suspect that this is probably a maximum for this point. Okay? To check this, you move in the direction of the gradient. So this is the gradient vector, x sub 0, y sub 0. So you fix an epsilon positive. This is how precise you want your answers to be. So move in this direction a distance of epsilon times gradient of f x sub 0, y sub 0. Well, here I was planning to divide it by its length, but you can choose epsilon even smaller, so that will count for dividing it by this length. So you will be somewhere here. Okay, so now you are here at x1, y1. Okay, so this is easy to do because I have one point to write the equation of this line. I have the direction of the line, so you write it parametrically, and if you make your parameter epsilon, then you'll stop somewhere here. Now you repeat this. Okay, now repeat. Move by epsilon in the direction of now we have a new gradient at a new point. Okay, so let me make this drastic. It doesn't generally change this much, but now the gradient is in this direction. Next time you are here. Now you are here. Okay, so let me say repeat. Well, again, if you want to be a good programmer, you have to put a stopping criteria for this, but in normal life you don't. You just let the program run, you just watch the results, and after a while you see that something is recurring, so you stop the program there. So this thing will move like this, and typically what happens is you go and at some point it starts turning around something here. Okay, so it means that the actual local maximum, maybe there are larger things, but this is just like fishing. You want to fish some fish, but then you may catch some other fish. So maybe your epsilon is not small enough to catch this one, but you turn around this, so you stop there, and then maybe take epsilon smaller. It depends. Maybe if this is already small enough, you choose a number here, and you say this is large enough for me. Okay. If you suspect that there are other local maximums, you can start from another point. So you see, you can also do this for the minimum. All you'll have to do is now, instead of moving epsilon in this direction, you move minus epsilon in that direction. Okay, so this is an application, but it won't show up in the exam, so that's why it's very interesting, because you can't do these calculations in the exam. So in the exam, this will be part of a question if you are curious where this may show up. Okay, so I think that's all we want to talk about directional derivatives. Well, we did this with two variables because the picture is easy to draw with two variables. If we have three variables, then the domain is the space. The function takes values from here and goes to another R. But the same thing will happen, except that now there are more directions. In two dimensions, I can just draw arrows like this, and it's easy. But if I want to draw this x, y, z, you see I have to use some perspectives to convince you that there are other directions. So it's just the same thing for n dimensions. So let me just write the expression for n dimensions. So we acclimatize ourselves with the notation. So in n dimensions, okay, so directional derivative of, in the direction of this, of x, x1, well, here, now, since there are too many things, we just denote the point by p sub 0, okay? So this is defined as the gradient of f. So we know what the gradient of f is, okay? So let me remind you what this is: a vector derivative of f respect to x1, and I'll evaluate it at p sub 0. Derivative of f respect to xn, I'll evaluate it at p sub 0. So I get a vector like this times the unit vector. Okay, so this is my unit vector in Rn. Okay, so this is the definition. Okay, so you see, once you discover the concept, then to write it down is easy. Okay, so I think that's all I want to talk about directional derivatives. So what else do we have? Okay, now we can come to tangent planes, etc. Okay, let me start from something new. Okay, now we want to look at tangent planes of surfaces given by, okay, now I write this like this: x, y, z equals 0. Okay, so sometimes sometimes a surface is given by z equals f of xy. Okay, so this is the easier way. Okay, so when you describe it like this, then your function is nice. If this is the xy plane, the surface is above that as a one sheet. But sometimes the surface is more complicated, and we even have simple examples. Consider the sphere. Okay, so the sphere, the domain of this function is the circle in the xy plane, but above xy plane you have a sheet here and a sheet here. So instead of writing these sheets separately, you just write x squared plus y squared plus z squared is equal to the radius square. Okay, so we prefer this one, but this is a special case. So how does it translate to this one? In this case, f, x, y, z is generally written like this: minus z. Equals 0 is the surface. Okay, so you can also write this, of course, z minus f, but after you do some calculations, this minus, if you keep the minus in front of z, your calculations look better. Okay, so that's the only reason you prefer this. Otherwise, you can write it as z minus f. Okay, so we decide to consider this one. Okay, so we want to understand the tangent plane at p sub 0, let's say x sub 0, y sub 0, z sub 0. Okay, so we remember our discussions before. Not every function has a tangent plane. So we want to work with functions which have tangent planes. We technically define them as differentiable functions. So we start with nice functions. Okay, let f be a differentiable function. Okay. Now there will be a tangent plane at this to this thing at that point if at least one of the partial derivatives is different than 0. Okay, so this is not covered in calculus. Now I am talking to you from advanced calculus plus a little bit of differential geometry. Okay, so there will be let's keep this as a remark. I'm writing this so that you feel comfortable about these things, because otherwise things look like magical formulas that drop down from the sky, but they are not. They are all derived from reasonable considerations. One thing you find out is the following. There will be, or there is, a tangent plane to the surface at p sub 0 if you calculate the gradient of f at p sub 0, and this is not all 0. At least one of the partial derivatives is different than 0. Okay? So again, this tells us, I will use this later on, so this tells us that locally, so locally in mathematics means that around this point there is some small neighborhood. Okay? Locally, the surface looks like an open disk, a disk, let's say, looks like a disk, okay, in R2. Okay, so here I'm, okay, so for example, again, let's look at the sphere. Okay, so the sphere, of course, is not a disk, but at every point you can find a nice way of saying that, okay, this is curved, but I can find a nice function from this curved part to a, say, disk of radius, small radius. Okay, so all the points here are in a nice way one-to-one correspondence with the points in the disk. With the sphere, you can do this very easily. Wherever you are looking, just project it vertically down. So if you are here, now you project it over here. Okay, so wherever you are looking, there is a way you can project it to the next coordinate plane, and all the points here map one-to-one to the surface. Okay, so that's what I'm trying to show here. We can do this also with the circle. Let's say n equals 1. So in a circle like this, okay, example, a circle. So this is very simple, but the idea is the same. So for example, here I can take this part, for example, okay, so project it down. So you see that this part is exactly like this part. Any point here corresponds to a unique point here, and any point here corresponds to a unique point here. So you parameterize this, and well, this is how you parameterize it. When you want to do calculations here, you do calculations here. But with this, the circle is very simple. So we don't use this parameterization for the circle. We use the angle parameterization. So any point on the circle is radius times cosine theta, comma radius times sine theta. You see, theta is between 0 and 2 pi. 0 and 2 pi is a straight line. Okay, so we parameterize this as a straight line. But 0 and 2 pi corresponds to the same point here. So we throw that point out. Then this point remains open. But then you can choose another way of doing this with theta. You can parameterize it like this. So that is also covered. Okay, so all of this is possible. Well, in this case, it is possible because we see it. But in higher dimensions, it turns out that this is possible because the gradient vector is not the 0, 0 vector. Okay, so this is not something that we do in calculus, but this is where it comes from. Okay, so what does it mean then? I can parameter, since it looks like an open disk, a disk in R2 in this case, it means that I can parameterize this surface by a disk. Okay, so let me mention this. Okay, so this means we can parameterize the surface locally around p sub 0. Okay, so the surface is something strange like this. This is p sub 0, but there is a small part here, and here in the plane we can take a disk like this, and we have this function, let's say phi, so that it looks scientific, x, y, okay. So any point here, so suppose 0, 0 goes there, phi of 0, 0 is p sub 0, and phi of x, y here is say phi 1 of xy, because this is in 3 dimensions. Okay, so this is in 3 dimensions. Okay, so maybe I use st here so that I can write here x, y, z. So suppose this is st. So phi st is, there are 3 functions. Okay, such that, now this parameterizing means that these points will lie on the surface. How do we convince algebra that these points will lie on the surface? These points must satisfy the equation of the surface. Okay, so such that f of phi 1 st, phi 2 st, phi 3 st equals 0. Okay, so try this with the sphere. You'll see that you can find easy functions like this locally. Don't do it to cover all of it. Just we are interested only at one point. Suppose we are at the north pole of the sphere. So you see that you can just send points from here to the north pole. Let me just write one example with the sphere. Okay, so we have this sphere like this. Okay, so points here. So first of all, this is x squared plus y squared plus z squared equals r squared. Take a point here. Okay, so the point here is your xy 0, but now I'm considering it as like this. So it will go to, so this point goes to x, y, and here square root of r squared minus x squared minus y squared. I choose the plus one so that I'm up here. If I choose the minus square root, I'll be parameterizing this part. Okay, so my phi 1 is this, my phi 2 is this is my phi 3. Just for convenience, instead of s and t, I just wrote x and y because we'll use x and y. Okay, so you see the idea is very simple. So what is a little bit deep here is that you have to prove that this holds in any dimension. And the only thing that makes this tick is that the gradient is different than 0. So this is the only thing that's beyond calculus at this point. Yes?
Meaning gradient 0 means that there's a local maximum.
No, gradient 0 means that there is a singularity there. The function has a pinch there. There's a pointed part of the surface so that anything you put there will be a tangent. Okay? So for example, try this one in the plane. So f x y. This is y squared minus x cubed. You draw the graph of this when this is equal to 0. So it will be a curve like this. And you see the gradient will be x and y. So at this point, the gradient is 0. Okay, so this is a bad point because geometrically, what do I expect from a tangent line? It will touch the point only at that point. Okay, but this one, they all touch the surface there. There is not a unique tangent line. So gradient equals 0 generalizes this idea. Okay. I don't hear, right? We are in R3, we have x, y, z parameters. If we define a relation between these three things, then it means that one of them depends on the other, so we have a surface. Okay, so the example is this one. Okay, this is our big fxyz minus r squared equals 0 is a relation. Okay, but we know that this is a sphere, a two-dimensional object. Three of them cannot be free because they depend on each other. One of them can be expressed in terms of the other. You see here. Okay, but you see I carefully chose this one of them in the upper part because if I choose it to be this point, then the directional derivative will be 0 for z. Okay, but that's again something that I don't want to enter. You can write z in terms of the others if the last part is different than 0. You can write y in terms of the others if this one is different than 0. This is the implicit function theorem, which you will see if you take advanced calculus. the name advanced calculus is invented to make it look scary, but it is just functions of calculus of several variables. Okay? Except that if you notice that in this calculus we will talk about functions of several variables, but all the problems we have are somehow reduced to one parameter. We restrict the function to a line, we take the derivative, well, that's one variable. Okay, so in all these things, there is always restricting things to one variable. We'll do multiple integrals, but there is a Fubini's theorem which says that you can integrate this one by one. In advanced calculus, you say, okay, now let's look at the other cases. Now we don't consider anymore what happens when you restrict it to one parameter. You let your parameters vary around, and you do calculus. Okay, but to make it sound scientific so that everybody will impress, we call it advanced calculus. Actually, it's just calculus of several variables. Okay, and these topics are covered there. So I'm just telling this to you so that you know that these things follow logically from basic considerations. They are not just magics. Okay, so now I forgot what I was telling, but okay, because in a minute we are going to say that I want to consider all possible directions here. Okay, how can we do that? It is because of this. Here I can take any direction. Okay, so let me do this. Here I can consider a direction like this. If I take this straight line here, it will be a curve like this. Okay. So this straight line will correspond to a curve like this. What is the tangent vector of this line? So okay, now this is differential geometry. You separate the curve and its tangent directions. So the tangent direction of this line is again something like this, but tangent direction is always a straight line. That corresponds to a tangent direction like this. Now this is a straight line. Okay. Now you see from this parametrization, okay, now I remember why I mentioned you this parametrization. From this parametrization, now you can convince yourself that all possible directions here will be covered. Okay. So I can turn this around, I can cover all possible tangent directions, and they all match here since these two shaded regions are isomorphic. Isomorphic means they have different names, but they are the same. Okay, it's just like two triangles being congruent. You can color one of them red, color the other green. They look different, but in general parlance of mathematics, they are isomorphic. Okay, so these two shaded regions, even though this is curved, this is flat, they are isomorphic through this nice function, whose existence is guaranteed by advanced calculus. Now I can cover all directions here. Okay, so now that we are convinced that we can cover all directions, now we can talk about what happens. Now I have I have this parametrization. Okay, I send it here. Now I consider the parametrization of this red curve here. Okay, so the parametrization will be like this, except that S and T are restricted to this line. So now we don't have two free variables. Okay, so in this case, for example, T is equal to S. If I do it like this, I have just one function, one variable. So phi 1 is a function of T, phi 2 is a function of T, this is a function of T. And it must satisfy this condition because this red curve lies on the surface. That's what I write now. Okay. So in your calculus book, it starts from here. I just explained to you that it is not magic. This is why the book starts from there. Okay. Now consider a parametrization of this red curve on the surface. Okay. So let's suppose its parametrization is like this. Now I'm using suggestive language, the position vector. Okay. So since S and T depend on each other, I have a line here. There's only one parameter. I called it T. So this is say R1T, R2T, R3T. Okay, so this point RT lies on the surface f of x, y, z equals 0. So it means that these expressions, when you put it here, they will lie on the surface. Here, to be absolutely correct, I have to say that t is in some neighborhood like this, because I cannot parameterize this globally. Consider the surface here, okay? With this parameterization, I can parameterize the northern hemisphere, but if I go down here, now it doesn't reflect the parameterization anymore. So the parameterization has a restriction. That's what we mean when we say locally. And most of the time, it is not important how large or how small you take it. The important thing is around this point, you can do it. Okay? So our point is p sub 0. So this means this lies on the surface. This means f of r1t, r2t, r3t is equal to 0. T is in this one. And we also translate that at t equals 0, this thing passes through the point p sub 0. So we also translated that. Okay, so now we are at one of those points in calculus when we run out of ideas. When you run out of ideas in calculus, you take the derivative of both sides. Okay, that should suggest something. Okay, so I have something here, so let's take the derivative of both sides, see what happens. Okay, so this is a composite function. Chain rule is required. I take the derivative of this. So take the derivative of both sides of this with respect to, well, we have only one parameter, t. So the derivative of f respect to x with respect to t at t equals 0, so that I don't write one more line. Okay, I can take the derivative with respect to t here and then say put t equals 0. So we are grown up, so let's do it in one step. I take the derivative of this with respect to x, then I put t equals 0. When I put t equals 0, I get p sub 0. So I evaluate this at p sub 0 and multiply this. Now I look at which expression I see standing for x. I take the derivative of this with respect to t. This is r1 prime t. I put t equals 0. Okay, and then I do this with all other variables. R2 prime 0 plus f z p sub 0 r3 prime 0 equals 0. Okay, so that's the nice thing about taking derivatives. Now we stare at this. It's a dot product of two vectors. So this is equal to gradient of f at p sub 0, and I multiply it with this vector. But I recognize this vector. This is the derivative of position vector. Derivative of position vector is velocity vector. Okay, so this is velocity vector at 0 equals 0. Okay, here this is t equals d dr r of t is velocity vector. It is tangent. It is tangent to the curve r of t at wherever you are evaluating this. Okay, so it turns out that in our calculation, this green thing turned out to be the velocity at 0. Okay, that's the tangent vector. So this is tangent vector to the red curve at p sub 0. Okay, so again, this dear friend shows up here. It doesn't care which curve you are calculating at that point. It just gives you a direction. Okay, and then whichever curve you are calculating here, and that's the reason why I gave that long talk about this parameterization. Here I can consider all possible tangent directions. Okay, so if you just read your book, it is not guaranteed. It doesn't say anything about this. It gives you just one parameterization here. Can we do it? Yes, we can do it. And it tells you that the gradient vector at this point is perpendicular to the direction in a directional tangent at this point. Okay, and then the book suddenly says that whichever direction you take, it is perpendicular. It is true, but then in your mind you must ask, is it possible that I can find curves whose direction is in this direction? Okay, so if you want to do this, it turns out solving differential equations, which is tough. So all these things are done. Yes, you can do it. Okay, so now let me rewrite this expression. Okay, now we run out of ideas again. There is no place to take derivatives because we have a constant. So at this point, you sit down, stare at it, and say, what does it mean? Okay, forget about all the calculations, forget about all the restrictions. This is what it means. At one point, I can choose any direction tangent to the surface. Okay, the gradient is always perpendicular to that. Okay, so the gradient is perpendicular to the surface. That's how we summarize this. Actually, the surface is something curved, so there is no such notion as a line being perpendicular to a curve, but what we mean is it is perpendicular to all tangents at that point. Okay, so let us write it down. Okay, so and that is going to give us a way to calculate tangent planes. Gradient vector of f at p sub 0 is orthogonal to every tangential direction at p sub 0 on the surface given by p, x, y, z equals 0. Okay? To every the tangential direction at p sub 0, we have a name for this. Well, we have to give it a name because you see that this phenomena this phenomena is so fundamental that it will show up over and over again. So we better give it a name. We call it the tangent plane in this. Actually, we call it the tangent space at that point, but we dropped the word space in calculus. We call it the tangent plane. The tangent plane at p sub 0 on the surface f of x, y, z equals 0. Okay, let's pause for a second. This is generally the question you ask in science, engineering. When you succeed something, you say, did I use everything I used? Were they all necessary? What is the thing that I kept using? I drove these pictures in our tree. I had 3 variables, x, y, z, etc. Okay, what if I have 5 variables? Will I have to develop a new technology? Okay, I'll look at this. This sentence depends on this equation. Gradient of f is defined for any number of variables, and this is just a vector. Okay, on the surface, a tangential direction on the surface. So whether we have 3 variables or 33 variables, it doesn't matter. This is true, but then of course this word plane has to be changed. Normally you call it the tangent hyperplane, or by abuse of language you can still call it tangent plane, but then the technical word is tangent space. Okay, because the dimension is high. Okay, so now we can write the equation of the tangent plane, going back to tree space, tangent plane to the surface at that point. We need 2 information to write the equation of a plane, a point where the tangent passes, p sub 0, and a direction which is orthogonal to the plane. Well, this is gradient. Okay, so these 2 pieces of information tell us that we can easily write the equation of the tangent plane. Okay. Now we can write the equation of the tangent plane to f of x, y, z equals 0 at p sub 0. So normally, well, we just say the equation, but we know that You can multiply this equation by a constant. It's still the same equation. So an equation for a tangent plane is not unique, but it's not very different. They all differ from each other by a multiplicative constant. Okay, so we need a point where the plane passes. Okay, so P sub 0, we want this plane to pass from P sub 0. A direction orthogonal to the plane. Okay, so here it is. We found that we interpreted this by saying that this is orthogonal to the tangent plane. So it is here, gradient of f at P sub 0. Now we write the equation. Okay, so the equation is gradient of f at P sub 0 dot product P minus P sub 0 equals 0. This is the equation. Okay. Any questions? No questions means either you didn't understand anything or you totally grasped it. So being an optimistic, I assume that you totally grasped the idea. So we stop here and take a break.